Hey, good morning, everyone.
Good morning.
Yeah, thank you for your presence. Today, I'm so happy to teach this session on machine learning for climate data science. I'm Shaolin Li. You can call me Sean. Currently, I am a postdoc at LEAP and also at Data Science Institute. My background is in fluid mechanics and hydrology. However, I also get a master in computer science from Duke as well. Before that, I was a master student at Cornell in mechanical engineering, where I also have some stuff in robotics, machine learning, and that. And long time ago, I was a student at Northwestern University, majored in environmental engineering. So I'm very happy to teach this session today. Uh, Okay, so before we dive into the technical material today, I would like to briefly walk you through how today is structured, so you know what to expect and how the pieces fit together. This morning, we will start at 9 a.m., which is now, right? Oh, well, we'll begin with session one, introduction to neural networks. The goal here is to understand the basic building blocks, how machine learning network is built and what are the mathematics behind it and why they are useful for Earth system model. After a short break, we will continue this discussion and move directly into a hands-on lab where you will apply neural networks to local climate data in the cloud. Whenever you have any question, just like raise up your hands and yeah, let me know. Um, so after lunch, we will shift focus to session two, convolutional neural network, CNN. CNN are like particularly important for Earth science because much of our data is spatial, maps, grids, and fields, right? Those CNNs can give us a way to encode the structure into the model. In the early afternoon, you will work through a CNN-based lab focused on forecasting global temperature patterns. This is a realistic example of how those tools are used in practice, including the limitations. Later in the afternoon, we'll transition from space to time with a discussion of recurrent neural network and then hands-on LSTM lab. This will help you think about sequential data, memory, and temporal dependence, which are central to climate and environmental systems. We'll wrap up the day with some final thoughts on generative machine learning. Not to go very deep into the math, but to give you a sense of where the field is heading and how those ideas connect back to the uncertainty extremes and physical modeling. So overall, today alternates deliberately between concepts and practice. If something feels challenging in the lecture, the lab is usually where it clicks. And if something in the lab feels confusing, there's a time you need to ask questions. Okay, now let's talk about like neural network. So to motivate neural networks, people often start with an analogy to how the brain works, right? This analogy is inspirational, not literal, but it helps frame the basic idea. So in the brain, thought and perceptions emerge from the firing of neurons. Individual neurons are simply a simple unit, but they become powerful because they are connected to many other neurons through synapses. When a neuron fires, it sends an electrical signal that propagates through these connections. But not all connections are equal. Some synapses transmit a signal strongly, others weakly. Some require a large stimulus before they activate at all. This idea of an activation threshold is essential. So neurons don't respond linearly to everything, they respond selectively. Learning in the brain happens through plasticity. Synapses change their strength over time based on experience. Connections that are useful get reinforced, others are weakened. Importantly, the structure stays mostly fixed, but the strength of connections evolves. The scale here is enormous. The human brain has on the order of like 10 to 11 neurons and 10 to 14 synapses. No single neuron is particularly intelligent, but collectively, they produce a remarkably complex behavior. So neural networks in machine learning borrows only this abstract structure and idea, simple units connected together with adjustable connection strengths and nonlinear activation. They are not biological models of the brain, of course, but instead, they are mathematical systems inspired by the distributed computation where learning corresponds to adjusting connections ways to improve performance on a task. This figure here shows a biological neuron. The dendrites receives signals from other neurons here, right? The cell body like combine these signals. If the combined signal is strong enough, then the neuron activates. The signal then travels along the axons to other neurons through synapses, shown from this image. So learning happens at the synapses. Synapses can become stronger or weaker, which changes how much influence one neuron has on another. Neural networks in machine learning are inspired by this idea. We keep the basic structure. We have input, combination, and output, but represent everything with numbers and equations. Okay, so the brain is not uniform. So different area of the brain performs different functions, of course, but some regions appear to have similar roles across most humans. Other regions are more plastic, meaning the function can change with experience. We still don't really know how specific functions are assigned to different parts of the brain or how those roles developed over time. Learning and experience clearly plays a role, but the full mechanism is not understood yet. Most importantly, even with all this structure, we do not understand how those neural systems produce that what we call a consciousness or thought. This is where the analogy to neural network stops. So in machine learning, we don't try to model consciousness. We focus on building systems that perform specific tasks. Okay, like neural network originally came from attempts to mimic how the brain works, at least at a very abstract level. They were widely used and studied in the 1990s and early 1990s, but interest declined in late 90s. At that time, models were limited by data, computing power, and training methods. So in the last decade, neural networks have seen a strong resurgence with more data, faster hardware, and better algorithms. They are now state of the art for many applications. So it's important to be clear, though, artificial neural networks are much simpler than the real brains. They are mathematical models designed to solve specific problems, not realistic models of biological intelligence. Okay. Now let's have a look at the neural network structure we modeled in computer science. So this is simply a neural network model called a perceptron. On the left, we have like input labeled at x1, x2, and xm, right? Each input has an associated weight, w1, w2, and wm. This weight tells us how important that input is. First, how does neural network calculate these strengths? So first, we take a weighted sum of the input, okay, shown here, right? Mathematically, it's the sum of the input times the weight, okay? You get a sum sign here. Next, we pass this sum through a nonlinear activation function here. This nonlinearity is very important. So without it, the model would just be a linear combination, right? So it's a linear function because like when you have multiple linear equations, you add everything together, it's still like linear. So it cannot model like selectivity. That's why we need an activation function. The result is the output, which we already denote as y hat. This output can represent a prediction such as a class label, for example, it's math or physics class, right? Or a numerical value, for example, how many grades you got, like in this class, 98 or 99, right? This entire process, input to output, is called forward propagation. Okay, here, forward propagation. In larger neural networks, we simply stack many of these units together, then we get like a network. Okay. Now, this is the same perceptron, but now we have a new term, which is W naught. We call it bias term. The input x1, x2, and xm are each multiplied by their weights, right? And summed. Okay, we get this equation. Now we have to add a constant term W naught, which is the bias. The bias allows the neuron to shift its activation. Whenever you have like a constant term, right? It's like moving the equation up, down, or left, right? It's like a shift. Okay. Even though like if you have like a zero input, you still have a constant term that you can move the network. Okay. So full expression is a weighted sum plus bias followed by a nonlinear, again, activation function. The result is the output y hat. So in one line, what we have here is multiply, sum, and add bias, then nonlinearity. We get output. It's very simple, right? This is how like one perceptron works. Okay, now we can try to like model this perceptron in a more like formal way. We can write like using vectors shown here. So instead of writing each input and weight separately, we collect the input into a vector x here, and the weights into a vector w. The weighted sum becomes a dot product. Okay, you have here like x transpose times w, right? In linear algebra, you get the equation. You can solve it easily. Okay, we first have this dotted product. Then we can apply the activation function g here to get the output. So we have a full model, a dot product plus a bias followed by a nonlinearity activation. Okay, this vector form is what we use in practice because it is efficient and easy to generalize into many neurons. Any questions so far? Okay, great. So after computing the weighted sum and adding the bias, we apply an activation function shown here at G. This activation function, as we mentioned, introduced nonlinearity. Without it, the entire neural network would reduce to a linear model, right? So no matter how many layers we stack and how many neurons we add, it's still like a linear function. That's why we need this nonlinear function. So one common example is the sigmoid function shown here. It maps any real number to a value between 0 and 1. So if you have a look at this equation here, right? If it's linear, you have like a sloped line, but like now you have like a curved structure. So this is a sigmoid function introducing the nonlinearity in this equation. So how do you understand this equation? So you can think of it as a soft threshold. Large negative values gives values close to 0 here, right? In this end, sorry. In this end, you get like zeros. Then large positive input will give you values close to 1 on the other end here. So different activation functions exist, but the role is always the same. They are working to allow the network to model nonlinear relationship. Now let's have a look at the different activation functions shown in this slide. These are three common activation functions you will see later in the lab and when training neural networks. The left one, again, is the sigmoid function. It maps input to values between 0 and 1. It was used heavily in early neural networks, especially for probabilistic output. In the middle is the hypertangent function. It's similar to sigmoid, but its output ranges from -1 to 1, and is centered at 0, right? This often makes optimization easier than sigmoid. On the right, this one is ReLU, the rectified linear unit. It outputs 0 for any negative impulse and grows linearly for positive impulse. So ReLU is simple, efficient, and widely used in modern deep neural networks. All of these functions, of course, are nonlinear, which is what gives neural networks their expressive power. The choice of like activation function affects the training behavior, of course, but the overall role of the activation function is the same, which is, as we mentioned multiple times, to introduce linearity, right? Now let's have a look at like the effects of the different activation functions. So as we mentioned, the purpose of activation function is to introduce nonlinearity into the network. Without activation functions, a neural network, no matter how many layers or how many neurons you have, would not behave like a nonlinear function, but just work as a linear function. Okay, so this figure shows a simple example. We have two classes of points, green and red. These classes are arranged in a complex pattern, right? So can we separate those points? Can we do it in neural network? Of course, we need to do it, right? So if without like a activation function, a linear model cannot separate these points with a straight line shown here, right? Because the boundary is not like a linear. There is no clear difference between the 2 points. It simply does not have enough flexibility. I mean, if we want to put it in a different way. So by adding the activation functions, the neural networks can build a nonlinear decision boundary shown here. Okay, this allows it to separate complex patterns like the one shown in this right figure. So activation function, what gives a neural network the ability to solve real-world and nonlinear problem. That's the reason why we need to have like activation. Okay, now let's look at a concrete example. Here we have two inputs, x1 and x2, right? The weights are 3 and -2. The bias for W naught is 1. So we compute the weighted sum here. The result is 1 plus 3x1 minus 2x2, right? Any problem with the calculation? Okay. The expression is just a linear function of x1 and x2, right? So if we try to understand x1 and x2 in a 2D dimension, what does it respond to? Any idea? A line, right? So because it's 2D, just like x and y in x1 and x2 plane. Okay, so after computing this linear combination, we apply the activation function g dot to produce output y hat. So this single perceptron always represents a linear decision boundary. To model more complex pattern, we need multiple neurons and multiple layers. Okay, the figure here shows the same perceptron, but now from a geometric point of view. Okay, you have this, as we mentioned, the 2D plane and the curve here, right? The line is called decision boundary of the perceptron, but points on the one side of the lines are one output, point on the other side produce another output. And of course, they have different meanings, right? If for classification problem. The weights control the orientation of the line. If you change like 3 to 4, then the curve will become more sharp, right? The bias controls where the line is shifted. I mean, in high school math, we know that like adding a bias it acts like moving the curve up and down, right? So a single perceptron separates space using a straight line. Now, if we want to represent the curved or more complex boundaries, then we need to introduce a activation function and multiple perceptron in different layers, right? Okay, now let's evaluate the perceptron at a specific input. Assume we have the input vector x equals 1 and 2. So let's plug this linear part into the model. What do we get? It's 1 plus 3 times minus 1 minus 2 times 2, right? The result is minus 6. Okay, so after this, the perceptron, the inner layer works. Okay, we get a value. Now, what do we need to do? We need to add the activation function g naught here, right? Okay, after applied the activation function, g minus 6 for a sigmoid function, as we shown earlier. Okay, what the result is about like 2 over 1,000, right? So geometrically speaking, this point lies well on the one side of the decision boundary, which is why the output is strongly pushed towards one class. I mean, like if you have a 6, you have -6, it's not very easy to see, right, how far it is. But if you have like a 0.002, then you will see it's far away from the curve. And that's why like activation function matters. So the perceptron works by computing a linear score, then scratching it with an activation function. That's like the mathematical reason behind it. This slide summarizes everything we have just covered. A perceptron takes input, multiply them by weights, and add a bias. These values are summed, then passed through a nonlinear activation function. The result is the output. This is the very basic building block of all neural networks. Every neural network, no matter how deep or complex, is built by repeating the same operation multiple times. Okay, so far you understand, right? A single neural network. Great. Now we can summarize the perceptron into two equations shown here. First, we compute a linear score, Z equals W naught plus sum of xj times wj, right? Okay, then what do? You apply a activation function G. That's it. So every neural network's layer is just many of these computations happening in parallel. Okay, now let's see. We move from one perceptron into a single layer neural network. The input are the same as before, but instead of feeding them into one neuron, we feed them into multiple neurons in parallel. These neurons form the hidden layer here, shown in the pink. Each hidden neuron computes its own weighted sum and applies an activation function. So each one represents a different linear combination of the inputs. The output of the hidden layer are then combined to produce the final outputs. So even just with one hidden layer, the network can represent much more complex functions than a single perceptron. So the key idea is still simple. Multiple perceptrons working together create more expressive models. Any questions with this slide?
You only use the activation function at the final output, or do you have an activation function at each hidden layer?
Yeah, that's a very good question. So technically, like you can just use activation function before the out layer, but in practice, what we do is we use activation after each layer. Okay. Great. Okay, next one. Here, the network produces more than one output. The input goes into a hidden layer, just like before. Each hidden neuron extracts a different feature from the input. Those features are then combined to produce multiple outputs. Each output has its own set of weights and own prediction. This setup is useful when we want to predict several quantities at once, such as multiple variables or multiple classes. So structurally, nothing is new here. We are just like repeating the same perceptron operation for each output. Right? A deep neural network is just an extension of what we have already seen here. Instead of like one hidden layer, we stack many hidden layers on top of each other. Each layer takes the output of the previous layer as input. Okay, so you have like a flow here. As we go deeper, the network can learn more abstract structures of the data. Early layers tend to capture simple patterns, while deeper layers combine them into more complex ones. Structurally, nothing fundamentally new is happening. Each layer still performs the same operation. You have like a weighted sum, activation, and output, right? We have repeated multiple times, and hope you can remember that. Okay, so depth simply gives the model more expressive power. Okay. Now let's do a case study here. So the question is like, will I pass this class? How do we do that? Okay. To measure whether you can pass the class or not, right? Usually, like people will give you a probability, say you have like 80% based on your past efforts and skills. So there is always a matrix to evaluate that, right? And we call this like loss functions. Okay, so suppose we want to predict whether a student will pass or fail a class. Each point here represents a student, okay? The horizontal axis is the number of lectures attended. The vertical axis is hours spent on the final project. So green points mean the student passed, red points mean the student failed. Our neural networks takes x1 and x2 as input and produce a prediction, pass or not, right? Of course, we want to pass. We want student to pass. But how do we tell the model whether its prediction is good or not? The role, that's the role of a loss function here. So it measures how far the model, the prediction is from the true outcome. Training a neural network means adjusting the ways to minimize this loss across all students. Okay. So suppose we have a new student shown by the purple point here. This student attended 4 lectures and spent 5 hours on final project, right? The question marks means we don't know the outcome yet. So will student pass or fail? The neural network, how does neural network works? It works, it takes the input 4 and 5, right? And produce a prediction, but the prediction might be right or wrong. Once we know the true outcome, we can compare the prediction to reality. Okay, the difference between what the model predicted and what actually happened is what the loss function measures. So the loss function answers a simple question: how bad was this prediction? Okay, we feed the input for file into the neural network. The network produces a prediction of 0.1, right? Okay, with selected weights, of course. This represents a low probability of passing because you only have like a 0.1 value here. But suppose the true value is 1, meaning that the student actually passed. So the prediction is clearly wrong, right? Okay, now the loss function takes these two numbers, the predicted value and the true values, and computes a single number that represents how bad this prediction is. If the prediction is close to the true value, the loss is small. But if the prediction is far away from the truth, then the loss should be very large, right? Training the network means adjusting ways to reduce this loss. Of course, loss function, we want to minimize it so that like your predicted result matches truth reasonably well, right? That's the goal here. But we don't just like compute the result for one student. We want to compute it like across the entire data set, meaning find the global minimum mean, right? For all data set, for all students. Okay, the loss function just tells us how costly a prediction error is. For a single data point, we compare the model's prediction and the true prediction here. We write this as a loss function. Okay, you have like this L here. F is the predicted and Y is the true value, right? Okay, so loss function takes these two values and returns a single number. That's the result of LFY. Okay, a good prediction always gives us a small loss, and a bad prediction gives a larger loss. Okay, training a neural network, again, means finding the way that minimizes this loss over all data points. Okay, so far, we have talked about a loss for one data point. In practice, we train on many data points shown here. You have multiple students, right? Each student attend like different classes and spend multiple different hours on the projects. So the empirical loss measures the total error over the entire data set. For each data point, we compute the loss between the prediction and the true label. Then we average these losses across all examples. So mathematically, this is written as a 1 over n, just like a mean, right? This again is a sum sign. All the losses you sum together, calculate the minimum, the mean value, okay? The quantity is also called object function in mathematics, or you call it a cost function, right? You're in projects, you have a cost, you want to minimize it. The same thing, which is here. We call it a loss function, cost function, or objective function. So training a neural network means choosing the weights W here because the model here is conditioned on W. We want to find a good set of W so that this loss is minimized, right? Is that clear? Okay, great. Okay, there is a common loss function for binary classification. Pass or not is like a binary problem. Okay, so what do we do? So usually we have a model output a probability between 0 and 1. Instead of give you an output like 0.1, 0.2, 0.3, right? You don't want a continuous value. You just give a discrete, whether it's 0 or 1. That's what we call classification problem. So this model will predict a value like 0.1 and 0.8, which we interpret as the probability of positive class. That's like before the output, right? So binary cross entropy compares the predicted probability and the true label, which is either 0 or 1. If the true label is 1, the loss gets strongly penalized and the prediction close to 0. If the true label is 0, then the loss strongly penalizes the prediction close to 1. So this loss function encourages the model to give high probability to the correct class and low probability to the incorrect class. This is why binary cross function is the standard choice for pass, fail, or yes, no problem. Okay, now mean square error is another loss function we used for mostly for regression problem. By regression, we mean like we have continuous value. We want to get a true value and continuously. We don't just want like discrete 0 and 1, okay? So for example, instead of predicting a pass or fail, we might predict a final grade. That's called like a regression problem. The loss measures the difference between the predicted value and the true value. We square this difference so that large errors are penalized more than small ones. Then we average the squared errors across all data points. So mathematically, it's the average of prediction minus truth squared, right? Mean squared error encourage predictions that are close to the true values, especially avoiding large mistakes. Now, training a neural network means finding the ways that gives the lowest loss. We define an objective function, which is the average loss over the entire data set, okay, shown here. The goal here, as we mentioned before, is to find a set of ways, W star, that minimizes this objective. The equation here just formalize that idea mathematically. So choose the weight that make the loss as small as possible, right? That's how we write it in math modeling. Okay, so everything we do during training is like to use gradient descent and backpropagation we'll introduce later, okay, to solve this optimization problem. So far, any questions yet for this objective function? Okay, great. Let's move to this slide just clarify what we mean by weights. The symbol W represents all weights in the networks across every layer. As we mentioned, like for a single layer, just have one hidden layer, right? But for deep network, you have multiple different layers. And for each layer, you have multiple neurons. And each neuron is connected to the input of the previous layer or the output of the previous layer. We call the input of this layer, right? With a weight. So W here just represents all the weights. So when we say we want to find W star, we are not turning one number, or we are turning, we are not like tuning one number. We are actually tuning like multiple parameters like at once for all layers and all neurons, right? Training means adjusting all of these weights together so that the overall loss is minimized. Okay, now I think like if you want to understand the problem like from a mathematic point of view, what you can do is to think about the loss as a loss surface shown in this image here. So each point on this surface corresponds to a particular choice of weights. The height represents the loss values. But the neural network are nonlinear. This surface, therefore, is not convex. You have many hills and valleys, and that means like you have many local minimum and local maximum, right? So our goal here is to find a set of ways you are moving like on this surface try to find a set of weight that gives a low loss, ideally close to the global mean. Okay, if you look at this surface here, like right at this corner and another corner here, and even the corner in the right, you got lots of minimum values. So the goal here is to choose one close to the, maybe like this one is a global mean. We want to find like a set of W close to give you a global mean, but like in practice, it almost impossible, right? Because like lots of hills and valleys. So you just need like a set of weights that gives you a minimum that is small enough compared to your control value. That's good enough. In practice, as we mentioned, we just need a solution that works well. You don't need to find the best solution, but a solution good enough to give you to answer your question. That's why optimization methods matter, and why training is not always straightforward. Okay, so training starts by choosing initial weights and bias. Okay, let's start from this cross sign here. We already pick these values randomly. We pick a point, often from a normal distribution. So on this plot, that corresponds to choosing a random starting point on the lost surface. Of course, you can randomly select the other points. If like lucky enough, you selected points around those minimums, right? So it takes less time to converge. But if you choose the large value here, okay, it takes time. But the starting point matters. That's because it affects which paths the optimizer follows and which minimum we eventually match. So the training does not begin from zero knowledge. It begins from a random guess that we then refine, right? Okay, so to decide how to update the weights, we compute the gradient of the loss. Okay, this is like, how many of you guys attended like calculus before? Okay, okay. So this symbol looks familiar, right? This is just gradient, okay? So the gradient tells us like which direction the loss increases fastest at our current position. So because neural network are nonlinear, this gradient is local. It depends on where we are on the loss surface and on the specific data we use, okay? In practice, we compute the gradients using a single sample or small batch of samples. We call this like a mini batch. The gradient is what guides at each step of training, okay? Now, once we have the gradient, we update the weights using the gradient descent method. So we take a small step in the opposite direction of the gradient, okay? If the gradient says like decreasing this line, okay, then we goes the other direction, right opposite, because we want to minimize it, okay? So on the plot, this corresponds to moving downhill on the loss function. We repeat this process, compute the gradient over and over again, then take one step, recompute the gradient and step again. Okay, this is how propagation works. So over time, this moves the weight towards a region of lower loss. Okay, now this slide summarizes the gradient descent algorithm. So first, we initialize the weights randomly, usually from a normal distribution, right? And of course, like if you have some knowledge about the weights, you can, of course, based on the knowledge, selected a reasonably good set of W, but more or less, in practice, we start with random distribution. Then we repeat the following steps until the model converges. We compute the gradient of the loss with respect to the weights. This tells us how the loss changes if we change the weights. Next, we update the weights by moving them into the opposite direction of the gradient. The parameter eta here is called learning rate, which controls how big the step is. For example, we said that we have calculated the gradient, right? We just need to go in the opposite direction. But like if that move is too big, then it becomes like a circulation, right, around the mean that you cannot reach the true minimum there. So you need a learning rate. That's why we have like an eta here. Okay, it's usually a value smaller than 1, right? But it like the smaller eta it is like the more stable the solution is, right? Because you are moving like step, and steadily. That means like you are more easy to reach the minimum value. But like if the bad thing is like if it's too small, then your propagation is very slow, right? It takes longer time to tune the model. Okay, so we keep doing this, computing gradient, update weights until the loss stops decreasing. The final weights are then selected as the training weight. Okay, this slide shows a very simple neural network. Again, the input X flows through the network, producing a prediction Y hat, which then gives a loss JW. The key question is, if we slightly change one weight, how does the final loss change? That's exactly what a gradient measures, right? Because the network is built as a sequence of operations, a change in one weight affects everything downstream. To compute this efficiently, we use the chain rule from calculus. This process, computing gradients by moving backward through the network, is called backpropagation. Okay, so to compute gradients, we use backpropagation. We want to know how changing a weight here, for example, W2, affects the final loss. The key idea is a chain rule. So a change in W2 changes the prediction Y hat. That change in Y hat changes the loss JW, right? So we break the problem into two steps: how the loss changes with the output and how the output changes with the weight. Backpropagation just apply this idea repeatedly, moving backwards through the network and one layer at a time. Okay, you see here. So we compute the gradient using the chain rule here. To find how the loss changes with respect to W2, we break it into two parts. First, how the loss changes when the output Y hat changes. Second, how the output Y hat changes when the output weights W2 changes. These two effects are multiplied together. Then, so the gradient is like changing in loss with respect to output, times change in output with respect to weight. Okay, you get this function. So backpropagation just apply this idea repeatedly, passing information back through the network. Okay, now you have two layers here. Okay, you get you have one layer here with respect to the output layer. You get like a chain solution here. Now we do the same thing for an earlier weight W1, okay? So a change in W1 will affect Z1 as well. The change in Z1 affects output Y hat, okay? That's like how this law is stamped. Okay, so the change in Y hat affects the loss JW. The effects of W1 on the loss passes through multiple steps. So we again apply the chain rule. The change in loss with respect to the output times how the output depends on Z1 times how Z1 depends on W1, okay? So backpropagation simply repeats this process, moving backward through each layer one weight at a time. Is it clear here? Okay, great. Now, for an earlier weight like that, okay, sorry. Okay, now from earlier ways, like W1, the gradient breaks into three pieces. First, how the loss changes with the output. Second, how the output changes with the hidden variable Z1. Third, how Z1 changes with weight W1. We multiply these three terms together. Each term is a local derivative, and backpropagation just passes these local derivatives backward through the network. So in deep networks, we repeat the same idea across many different layers. We apply the same process to every weight in the network. So for each weight, we compute how a small change affects the loss using the chain rule. Gradient from the later layer are reused when computing gradients for earlier layers, right? That's what makes backpropagation efficient. So backpropagation is not a new algorithm for each layer. It's the same rule applied repeatedly, moving backward through networks. Once we have all this gradient, we update all ways using gradient descent. Okay, this image shows what a neural network's loss landscape can look like. The loss is a function of the neural network weights. And in deep networks, this function becomes extremely complex. It has many valleys, ridges, and flat regions, of course. That's why training is difficult and why optimization is not guaranteed to find the absolute best solution. So in practice, we don't need the perfect minimum, as we mentioned before, for single layer. Okay, we just need a set of weights that gives low loss and good performance under the control for your answer, then that's enough. This complexity is also why choices like initialization, learning rate, and optimizer matters. Okay, so even though the loss function is complex, we still use gradient descent to optimize it. The update rule is shown here. The key parameter is eta. We call it learning rate, right? The learning rate controls how big a step we take when updating the weights. If the learning rate is too small, training is very slow. If it's too large, we can overshoot good solutions and training can become unstable. So choosing a good learning rate is crucial for a successful training, right? This plot shows what happens with a small learning rate. For example, like we have like a 2D function to express this loss in this curve, okay? We start from initial guess here, red dot. Because the step size is very small, then the optimizer moves slowly, okay, very slow, right? It may eventually go downhill, but it can also get stuck in a local minimum. For example, there is a local minimum here, okay? So while a small learning rate is stable, it makes training very slow and prevent the model from finding a better solution. So it's important to find a good value, either not too small or too big. Okay, this slide shows the opposite case, so a large learning rate. Okay, so each update step is very big. Instead of smoothly moving downhills, the optimizer overshoots the minimum. As a result, training can become unstable and diverge, meaning the loss function increase instead of decreasing. So while a large learning rate moves fast, it can completely miss good solutions. So learning rate choice really matters. One option is simple, but brute force. So try many different learning rate and see which one works best, right? That's when we don't know the real solution is from intuition. We try multiple values and until we get the best. But the second option is smarter. Use an adaptive learning rate that automatically adjusts during training. So modern optimizer follow the second idea. They change the step size based on the shape of the loss landscape and the gradient, meaning it's adaptive. Okay, to handle this, we no longer use a single fixed learning rate. Instead, the learning rate can change during training. It can become larger or smaller depending on how large the gradient is, how fast learning is happening, and even the size of individual weights. The idea is to take larger steps when it's safe and smaller steps when needed. This makes training more stable and more efficient, especially for deep neural networks. Okay, these are some common optimizer used to train neural networks. They are all built on gradient descent, but differ in how they adjust the learning rate. Here, the first one, momentum, helps smooth the update by keeping track of path gradients, so optimization doesn't get stuck oscillating. Auto ADA grad adapts the learning rate for each parameter, taking smaller steps for parameters that have seen large gradients. And ADA delta improves on ADA grad by preventing the learning rate from shrinking too much over time. And this one, RMS prop, also adapts learning rate based on recent gradient and works well in practice for deep networks. And of course, ADAM combines idea from momentum and adaptive learning rate and This is often a good default one in practice. You don't need to like memorize this. The key idea is to that like modern optimizer automatically manage step size to make training faster and more stable. Like you understand the notion, you understand the idea behind it, then you can like import the function from Python and do it for you. Okay, these two pictures show gradient descent with and without momentum. For example, on the left here, without momentum, the optimizer is that's a lot, right? You see like multiple curve hikes here. It keeps changing direction and makes slow progress towards the minimum. But on the right, with momentum, okay, as GD with momentum, it updates. The updates are much smoother. The optimizer keeps moving in the same general direction and oscillates are reduced. Momentum also allows us to use a larger learning rate while still remaining stable. You can think of it like pushing a ball downhill, right? It builds speed in the right direction and ignores small bumps. Okay, now let's like take a look at autograd and ADA grad and ADA delta. So ADA grad like changes the learning rate for each parameter. Parameters that are updated often get smaller steps. Parameters that are updated like rarely get like larger steps. This makes ADA grad useful for sparse data, where some features appear much more often than others. The downside is that like ADA keeps accumulating past gradients, so the learning rate can become too small over time and the training can slow down. ADA data fixes this problem. Instead of remembering all past gradient, it only keeps a recent window of the gradient. This prevents a learning rate from shrinking forever and makes training more stable. So technically, like ADA is one of the most commonly used optimizer in practice. Although some people mention ADAW, another version of it should be used. So the idea is the same. Like it combines two different ideas, like momentum, which smooth update using past gradient, and adaptive learning rate, which adjusts step size for each parameter. So ADAM like keeps tracks of the average direction of recent gradient and the average size of recent gradients. So you can think it like a heavy ball with friction rolling downhill, right? It moves quickly in useful directions, but slows down in noisy or steep regions. So because of this balance, Adam often works well out of the box and a good, usually used a good default choice. Okay, now this figure compares how different optimizer move on the same loss function. Click it again. Okay, so each color path shows the trajectory taken by a different method, starting from the same point. Plain SGD tends to zigzag and moves slowly, see here. Momentum smooths the path and moves faster. Methods like ADA grad, ADA delta, IMS prop, and ADAM adapts the step size and usually reach good solutions more efficiently. The key point is not which path is best here, but that optimizer choice affects how fast and how reliable your training is. In practice, ADAM or IMS prop are often good default choices. So far, so we have described gradient descent using the entire data set. That means for every update, we compute the gradient using all training samples. For large data sets, this can be very expensive and slow. Computing the exact gradient over the full data set at every step is often not practical. So while this version of gradient descent is conceptually clean, we really don't use it directly in practice. Okay. Now, in stochastic gradient descent method, we update weights using one data point at a time. Okay, so instead of computing the gradient over the full data set, we just pick a single training example, compute its gradient, and update the weights. This makes each update very fast and cheap to compute. The downside is that these updates are noisy. Each step is only an approximation of the true gradient, right? So the path can zigzag. SGD, stochastic gradient descent, trades accuracy per step for speed and scalability. That's like a trade-off here. Are those ideas clear here? Any questions? Okay, great. Now, let's talk about mini batch. So mini batch strike a balance between full gradient descent and pure SGD. As we mentioned, SGD stochastic gradient descent just pick one single point, but like a mini batch strike the balance between full and a single. Okay, so by using a small batch of data points, we get a more accurate estimate of the gradient than a single sample. This leads to smoother converge, of course, and allows us to use larger learning rate safely. At the same time, mini batch are very efficient. They allow us to parallelize computation, especially on GPUs. That's why mini batch training is the standard approach in practice. Okay, this slide shows three common situations. On the left is underfitting. Okay, so you have multiple points, right? You have like a very simple model. You only get a curve here, a linear curve that cannot describe the data set well because like the transition structure here is not learned. Okay, in the middle is ideal fit. Okay, you want a curve with good expressiveness so that better describe the trend of the points, right? On the right is the overfitting. Okay, the module is too complex and starts fitting random fluctuations in the training data. It performs well on the training set, but does not guarantee good results for your testing data set. Question? Yeah.
Is the business out, or is this more of a qualitative, like some interpretation?
So can you repeat it?
Are there metrics to figure out if you're underfitting or overfitting, or is this more up to the user?
Oh, okay, that's a very good question. So I think here the idea is like if you start with the entire data set, right, the computation is very costly. So, but instead, like if you use one single stochastic gradient descent, then that's too noisy, right? Because this point may not be a good representation of the entire data set, right? So what people do in practice is you find a mini batch. Let's say that we separate the entire data sets into different batches, and you just use one batch to do the calculation, right? You try to fit a function, use this small batch of data set, okay, and leave the algorithm to tell you whether this result is good or not. That's like what it works. Does that answer your question?
I was more sort of like whether or not you're underfitting.
Oh, yes. So that's what I'm going to talk about later. Like, how do we measure whether like the model is overfit or underfit? Okay, yeah. So far, like just from this image, we want to understand, yes, this is a good realistic curve, right? So the left side clearly is underfit, and the right one is overfit, right? You want your model to predict a result close to the middle figure instead of the other two, okay? So, I mean, like, how do you like formally describe this behavior, like whether your model is a good fit or not? We call it like generalization, right? Whether your model is a good generalization of the true behavior, or like, do you have any regularization to your model so that it's not overfitting the curve? That's like what we are going to discuss next. Okay, so regularization is a way to prevent overfitting. It does this by adding constraints to the optimization problem that discourage overly complex models. So instead of allowing the network to fit every small fluctuations in the training data, regularization encourages simple solutions. We use regularization because we care about generalization. However, the model performs on new, unseen data, not just like on the training set itself. Okay, so what are the regularization methods we have? So we will cover some following now. So the first one is like dropout. It's a simple and effective regularization method. By its name, just drop it out, right? So during training, we randomly set some neuron activations to 0. This means that in each training step, the network sees a slightly different architecture. As a result, the network cannot rely too heavily on any single neuron. It is forced to learn more robust distributed representations. At test time, dropout is turned off. The full network is used again. Dropout helps reduce overfitting and improves generalization. It's just one method of it. Okay, I think maybe we will stop here, have a break and come back later. Okay, okay, let's continue.
I think that's the next.
So we have a few slides left just for the first session. So after this, I'll have you work on the lab. Okay, so let's just pick up what we left with last time. So several different regularization methods. First, we have covered dropout. Now, let's go deeper. So during a training, dropout randomly selects some activation to 0, as we mentioned. That's the definition of dropout, right? So typically, we dropped out about 50% of the neurons in a layer because different neurons are dropped each time. The neural network cannot rely on a single node to make a prediction. That's why it works. Okay, this forces the network to spread information across many neurons and learn more robust features. So at test time, dropout again turned off. We use the full network. So this figure shows dropout in action. So some neurons are temporarily turned off during training, shown by the faded nose. Because different neurons are dropped each time, neural network learns to be robust and not depend on specific connections. Okay, so you can think of dropout as training many slightly different networks and averaging them together, right? So this help reduce overfitting and improve generalization. Okay, now early stopping is another strategy to prevent overfitting. So instead of training the network until the loss as small as possible on the training data set, we stop training earlier. We set a cutoff. So whenever your loss is around or smaller than this value, we stop. This is called early stop, right? Okay, now what we do in practice is we monitor performance on a validation set. When validation loss stops improving, we stop training. This prevent the model from continuing to feed noise in the training data. Early stopping is simple, effective, and often used together with other regularization methods together. Okay. The idea focuses on how weights are distributed across layers. If weights in some layers are much larger or smaller than others, gradient can either vanish or explode as they move through the network. So to avoid this, we try to keep the variance of weights similar across layers. This helps signals and gradient flow smoothly forward and backward through the network. So in practice, this is handled through careful weight initialization, which of course improves scalability. Okay, I think that's what we have for the first session. Now, if you have any questions, just raise your hand. If no, let's get to the lab. Okay, any questions? Very good. Now let's do the lab. I have uploaded it on Canvas. You can download there. Yep. And I also have mentors and TAs. Yeah, there. If any questions, yeah. Okay, also approach here. Yeah. So for the lab, you just download the data, download the script, and play with the code to see if you can generate the results on the Jupyter notebook. If not, ask this or discuss with your classmates on the table. Yeah, of course. Yeah.
Yeah, can you upload the lab, please?
Upload. Okay. To the slide. Okay, I'll do it.
Thank you.
Sure.
Hi everyone. Because some of you are struggling with this, I'm going to give some instructions. First is that by default, it be set to the base Pangeo notebook, but that's not what you want to use. You actually want to use this one, the Pangeo TensorFlow ML notebook. And the reason is that it comes with TensorFlow pre-installed. So for those of you who you tried to run the code and they said there's no TensorFlow, this is why. And after that, so after I start it up,
It takes time.
yes.
Okay.
Oh, okay.
Yeah.
Good.
Yeah, just go to like the initial page, maybe.
Okay.
Yeah.
Where is it?
Create a new one. I haven't uploaded yet.
Oh, okay. Sorry, the files are not here, but so in your folder, you have the 4 files that Sean uploaded after you. Make sure that this file called utis.py is in there as well. You will see in the code it says import star from utis. That is actually the utis.py file. So don't try and pip install utis. You will actually override the functions that you need and make sure that file is there. So yeah, I think this should solve the problem for many of you. And if you have already pip installed utis, you will need to restart your server. You can raise your hand. I can help you with it.
Yeah, thanks, dear. Okay. Hey, welcome back, everyone. Let's get to session 2. So this session, first, like, it's going to be like 45 minutes. After this session, you will have like a short break. Then we'll head to the lab session for convolutional neural network. Okay, so let's talk about convolutional neural network, or CNN. So far, we have treated input as just line vectors, right? But image and many earth science data sets have spatial structure. Nearby pixels are related, far apart pixels are much less related, right? So convolutional neural network take advantage of this. Instead of connecting every input to every neuron, convolutional neural networks use local spatial information. This diagram reduces the number of parameters and dimensionality of a problem. The key idea is simple. So use where things are in the image, not just what the values are. Okay. So to a computer, an image is just numbers, right? Each pixel is a number that represents intensity. For a grayscale image, this value is usually between 0 and 255. So an image is simply a matrix of numbers. For color image, we stack 3 such matrices together, one for red, the other 2 are for green and blue, right? So the image becomes a 3D matrix for colorful image. Neural networks don't see faces, clouds, or oceans. They only see numbers arranged in space. So in computer vision, we already map an input image to some kind of output. First, the image is represented as a grid of pixel values. That's what the network actually works with. There are 2 common types of tasks. Of course, the same regression, the output is a continuous number, like temperature, height, intensity, or grades, right? Classification problem, the output is a class label. Often the model produces a probability for each class, like the list shown here, whether it's Lincoln, Washington, Jefferson, or Obama. So the job of a vision model is to take pixel values and turn them into meaningful predictions. When humans look at images, we don't process every pixel individually. We recognize features. For example, for this image, like for faces, we notice things like eyes, nose and the mouth, right? For the middle image, like the cars, we look for wheels, headlights, and license plate. For houses, we recognize doors, windows, and steps. Convolutional neural network learns to do the same thing. Each layer detects simple patterns like edges and corners. Later layers combine those into high-level features like parts of objects. At the top, the network uses these features to make a final decision. So convolutional neural networks, CNN, learn features automatically from simple to complex directly from this data itself. So before deep learning, computer vision relied on manual feature extraction. The process looks like this. First, let's use some domain knowledge to detect what matters, then define the features by hand, and finally detect those features to classify image. You can look at the image in the left. So this approach, of course, is difficult because a real image varies a lot. Objects change with viewpoints, scale, lighting, background cluster, and occlusion, right? So designing features that work well across all these cases is very hard and requires a lot of expert efforts. I mean, like, even though like somehow we can distinguish features across these images, but it still takes time, right? And not efficient. It requires lots of efforts and time to do these classifications. So this limitation is what motivated the move towards learning features automatically with neural networks. Specifically, the topic we are discussing now, like convolutional neural network or CNNs. Okay, so the key question here is, can we learn features directly from data instead of designing them by hand? This is exactly what neural network works, especially like CNN. So at low levels here, like I see the left image, the network learns simple features like edges or dark spots, right? In the middle level, it combines those into parts of objects like eyes here or noses, right? So at high levels, it learns abstract concepts like overall facial structure. Those are like things that build in hierarchy from the neural networks. So each layer builds on the one before it. The more layer you have, like the more complex structure that CNN is able to detect. This hierarchy of features is learned automatically during training. Okay, now this is a fully connected neural network. So every pixel in the image is connected to every neuron in the next layer, right? This gives the network a lot of flexibility, but it comes with two big problems. First, it has a huge number of parameters, which makes training slow and prone to overfitting because you just have many neurons, much more than what you need to actually like represent the entire image. So second, it ignores the spatial structure. Pixels that are next to each other are treated the same as pixels that are far apart, because like in forward neural network FNN, what you do is you put like each pixel into that vector matrix, right? So like the relationship between the two closed or surrounding pixels are not exactly coded in the network. That's why like it doesn't work well for this and prone to overfitting. So while like fully connected neural network can work for small problems, they are inefficient for images. That's why we need a different approach, convolutional neural network. Okay, so in a fully connected network, the input image is treated as a vector of pixel values. Each pixel becomes one input feature. Every neuron in the hidden layer is connected to all input pixels, as is shown here. This means the network has no notion of spatial structure. Neighboring pixels and distant pixels are treated the same, right? It also leads to a very large number of parameters, which makes the model inefficient and prone to overfitting. These limitations motivate the use of like convolutional neural networks, which exploit spatial structure, like shown here. So here we use the fact that image have spatial structure. For example, instead of connecting every pixel to a neuron, we connect each neuron to a small local patch of this image shown in this red box. The neuron only sees the pixel inside the region. It ignores everything else. So for each like convolution, you just take this box, okay, and take the pixels in and say, okay, this is what our like neural network sees. Okay. By doing this, like we keep the local information, reduce the number of parameters, and of course preserve a spatial relation in the image. That's like the basic idea of a convolutional neural network. Is that clear? Yeah.
Yeah.
Oh, questions.
And when you do this, is this each pixel, is that box one pixel at a time?
Oh yeah, that's a good question. Yeah, we'll cover it later. Like that's like how we build CNN. Okay, this is like just like a basic information of how you get like the information from this patch. Okay. Now this figure shows how we extend the idea of local connections. We take a small patch of the input image and connect it to a neuron in the next layer. Okay. Then we slide this patch across the image, like you can go like from left to right or up down. Okay. Repeating the same operation at different locations. Each neuron looks at a different region, but they all use the same patterns of connections. The remaining question is how do we weigh the pixel in each patch to detect specific features? That's where filters or kernels come in, which is exactly where we'll look at next. Okay, so in convolutional neural network, we call this like a filter, like we use filter, and they also have like a fancy name called kernel to extract the features. A filter is just a small set of weights applied to a local patch of the image. Each filter is designed to respond to a specific kind of pattern, like an edge or texture. We use multiple filters so the network can detect different features at the same time. So importantly, the same filter is applied everywhere in the image. This is called parameter sharing. It means that if a feature is useful in one part of the image, it must be useful everywhere, like in the training. Okay, here's how convolution works in practice. So we chose a small filter in this, again, in this red box. For example, here we have like a 4x4 window with 16 weights. We apply this same filter to a local patch of the image, computing a weighted sum and get one output value. Then we slide the filter across the image here by 2 pixels and repeat the same computation on the next patch. This sliding patch by patch operation is called convolution. That's like how you understand like convolution, like from an image or geometrically. Like I mean, in math, what you do is you just flip the matrix, right? Then do the sum, weighted sum, like move one by one. But like from like an image, you can understand it this way. Okay, so using the same filter everywhere, it allows us to detect the same features at different locations. And by using multiple filters, we can detect multiple kinds of features at once. Okay, so let's look at the difference between the two images. So for us, right, it's just like 2x. Is that clear? Yeah, just like you rotate the image, right? You get a different version of x. But to computer, like it's hard for them, right? Because as we mentioned, like computers see those image as numbers. But now, like if you flip it, then like the matrix is different. So the computer like does not recognize it. So we need a way to figure out. The goal here is to build a model that recognize as x, like even though like we shift, rotate, or deform the value, like we should make sure that to the computer they're the same. Okay, so even though those two x looks different, at the pixel level, they share the same local features, right? So each X is made up of small diagonal patterns you can see here. Those patterns appear in different locations, but they are the same. They are the diagonal patterns. So CNN don't try to match the whole image at once. Instead, they detect these local features, small diagonal pieces, and then combine them. Okay, let's see how it works. Okay, we first detect a small patch here. Then we try to add those and combine those patches together. Okay, so as long as the same feature are present, the network can recognize the image as X, even if it's shifted or slightly deformed. This is why feature-based representation are so powerful in convolutional neural network. Is this clear here? Okay, great. Now, these small grids at the top are called filters here. So each filter is designed to respond strongly to a diagonal pattern, which is a key feature of the letter X. So when we slide a filter over the image, it computes a score at each location. If the local patches look like the filter, the response is large. If it doesn't, the response, we make it small, right? So different filters detect different diagonal orientations. Together, they can pick up all the parts that makes up an X. So instead of recognizing the entire letter at once, the network detects the pieces of X like one by one, then like combined together. So we have like a final a group picture for X. Now this slide shows exactly what convolution means. So we take a small filter and place it on top of a patch of the image. For example, we have like a green box here. Let's put it here. Okay. First, we multiply this filter to the element here. We do it like element by element. So each filter values times the corresponding pixel values. Okay. See, like 1 corresponds to the one here, right? So you get like you do the multiplication, you get a result which is 1 here. Okay. Then we add up those products together. A single number is the output of that location. For example, here, okay, after applying this matrix, you get like a new matrix, which is 1, 1, 1 here, right? Okay, identity matrix of 1, then you sum up everything together, you get a value, which is 9. And this is the output of this layer. So when we slide the filter to the next location and repeat the same process, we get like similar results. So let's summarize the process. Very easy, right? Convolution works by multiply locally, then sum the result, then slide, move to next location, right? This is how convolution works. Okay, now let's use a concrete example to show how convolution works. So on the left, we have a file by file image. On the right, we have like a 3 by 3 filter. We place the filter on the top of the image, starting at the top left corner. Let's do it from here, okay? Now, at each position, we multiply the filter and the image values element by element and do the calculation. Then like we can add up everything together, okay? Then get one output value for each calculation. The single value becomes 1 pixel in the output matrix. Okay, so what do we do next? We slide the filter like 1 step to the right, right? You can set the slide size, whether it's 1 or 2. So by default, we use 1 here. Okay, we keep sliding the filter across the image and then down until we cover all valid points. So convolution now becomes like slide the filter, multiply, right? Next step is sum, then repeat, right? Okay, so let's do an example calculation. So first, we place this 3 by 3 filter on the top of the image, okay? So it overlaps here. Okay, then we multiply each image value by the corresponding filter value, okay? Then do the calculation and sum all results together. So in this example, the result here is 4, right? Any question with the calculation here? Okay.
5.
5?
Only once.
Okay, let's do it here. Okay. So you have 1 here, right? 1 corresponds here, right? Okay, you have a 0 here, right? This 0 times this 1 goes to 0, right? So together you have 1, 2, 3, 4, right? So you have like a sum of 4, right? Then like next step is we can move this filter one step to the right, okay? And do the same calculation and repeat the process until like all cells like maps one filter placement to the other and finish the cross calculation. So I'll have you guys work on the second box here, like do the calculation and tell me your result. No? Okay. I'll give you like 30 seconds. So who has the answer? Yeah, three. Okay, three. Different answer? Okay, great. Okay, we have three. Okay. Okay, can you all work in group now, like, and finish all the empty box here? Yeah, I'll give you like one minute to do that. Hey, probably this is the only time that you are going to do the convolution by hand yourself. But next time, like people just use code to cross product. But like try it this time to make sure you understand the math behind it. Okay, let's back to the result here. You guys all get this number? Okay, let me assume yes. Okay, let's move to next slide. So each convolution filter produce a feature map as we just like did the calculation. So on the left now we have like an original image. When we apply different filters, we can get different feature maps. For example, we can sharpen the image. A sharpen filter enhance fine details. And here we have like an edge detection matrix, which will like highlight the boundaries. Then we also have a strong edge filter, which emphasize sharp transition even more. Okay, that's all depends on like how you design your filter. For different kind of like combination of the numbers, you get different features detected by this convolution. Okay, so each filter corresponds to a different pattern in image. A convolution layer does not produce one output. It actually produces many feature maps, each capturing a different type of information. These feature maps are what the next layers use to build more complex representations. Now, this, yeah.
With the operation tab here, are you sharpening the image and then applying the filter, or are these different filters that you're referring to?
Oh yeah, that's a very good question. So like here sharpen, we mean like this filter is a sharpening filter. So you like apply this filter to the convolution with the original image. The result is called a sharpened image. And this is what is shown here.
The output of the
Yes, yes. Yes, that's exactly what you did previously, right? You have like a filter. For example, this is a sharpening filter. We apply this to the original image, and we get this image. This image was called like sharpen. And here is edge detection and strong edge detection filters. Cool. Any more questions? Yeah.
For the strong edge detector, is it better for like vertical changes? Because like you can't, like her shoulder is like.
Oh yeah, yeah, exactly. Like it's all based on the filter itself. Like I mean, if you do the comparison, you can see that like but this one is like the second rows is like have values there, right? That's why like yeah, it gets like some kind of edges here, but like here if you put like the top row and the bottom row like to a value, then it becomes like more stronger like in filtering those edges there. But that depends on signal processing. I think like there's another course supposed to be discussing how many like how do you design a filter so that you can detach edge or detach the high pass signals better. Okay, but like feel free to check more that later. Yeah. Okay, so this slide summarizes what convolution does. We apply a small set of ways called a filter to a local patch of the image. We use multiple filters so the network can detect different kinds of features at the same time. And we share the same filter ways across the image, so the same feature can be detected anywhere in this image. These three ideas are what will make a convolutional neural network efficient and powerful. What are the three ideas? So locality, right? The multiple filters and the parameter sharing. Those three ideas are the basis for CNNs. Okay, now this diagram shows a full CNN pipeline for image classification. So we start with the input image. First, we apply convolutional layers. These layers use learned filters to produce feature maps that detect edges, textures, and patterns. Then after each convolution, we apply a nonlinearity, usually like the activation function we call like a ReLU, for example, to introduce nonlinear behavior. Next comes pooling. It means like downsampling the feature maps. Pooling reduces spatial size, keeps the most important information, and adds some robustness to small shifts. After several rounds of convolution and pooling, we flatten the features and pass them to a fully connected layer. The final layer uses learned feature to make a classification decision. Yeah, shown here in the last layer. So during training, the network learns the filter weights automatically from the image data. That's like how the pipeline for neural network is structured. Okay, in a convolutional neural network, neurons, as we mentioned before, they are locally connected. Each neuron in a hidden layer only looks at a small patch of the input image, shown here in the red. For that neuron, the steps are simple. Take the pixel values from local patch, compute a weighted sum, and add a bias, and you get a value. So that produces an output value. By repeating this across the image, different neurons respond to different regions, but all follow the same rule. This local connectivity is what follows CNN. Is what allows CNN to capture like spatial pattern efficiently. Now this slide shows the same idea, but now written mathematically, right? So for convolution, what it does is just like a two sum together here. So each neuron in the convolutional layer look at a small window of output, for example, a 4x4 patch. It multiplies each pixel in that patch by a corresponding weight in the filter, then add them together and add the bias, okay, B here. The sum is the neuron's output. So finally, we apply a nonlinear activation function to that. Then every convolution neuron is doing three things. Applying a small window of ways, computing a linear combination, then applying a nonlinear activation function. This operation is repeated everywhere in the spatial map. Now this slide shows how we think about the output of a convolutional layer. So the output is not just like a flat vector. Instead, it has three dimensions. For example, like height here, like depth and width, right? So height and width, those are like spatial dimensions. It's easy to understand, right? Just like in the image, you have like a width and a height, okay? But depth is like the number of filters you applied to that image. So each filter produces one feature map so that like then you stack everything together. So you have like a 3D image. So the output is has a size of h by w by d. The stride controls how far we move the filter each step. Of course, larger stride means a smaller output, right? Because like if you slide like every 2 pixels, okay, then you have like more image left, okay, but you have a smaller output. So the receptive field describes which part of the input image affects a particular output neuron. As we stack more layers, each neuron effectively sees a larger portion of the original image. That's like the result shown here. Okay, now after each convolution, we apply a nonlinear activation function. It's nothing like different, the same, the ReLU function, rectified linear unit. It works pixel by pixel. So if a value is negative, it becomes 0, right? Shown here in this figure. If it's positive, it stays the same, right? This is like a linear function here. But like the combination is a nonlinear operation. Without linearity, stacking convolutional layers would still behave like a single linear operation. ReLU allows the network to learn complex nonlinear patterns. You can see that after ReLU, the important positive response remains, but the negative signals get flattened, right? That's like the reason why like you need an activation function here. Okay, now after convolution and ReLU, we often apply pooling. So pooling is a downsampling operation. In this example, we use max pooling with a 2x2 window and a straight of 2. A max pooling means like, for example, in this matrix here, like it's 2x2. Okay, for this patch, we just find the max one. Okay, that is called max pooling. Or of course, you can use average pooling, right? Take the mean of those entries. Okay, this reduces the spatial size of the feature map, making the network faster and more memory efficient. Pooling also adds spatial invariance. Small shift in the input don't change the pooled output very much. So pooling keeps the most important information while throwing away fine details. Okay, now this slide shows what happens when we stack convolutional layers. So in the first convolutional layer, the network learns low-level features like edges and simple textures, right? So in the next layer, okay, we have like some like middle-level features. Those features combined, like we can see like eyes, ears, and nose, okay? And even deeper, in deeper layers, the network learns high-level features representing the entire object or structure. For example, like in this image, now we can see facial structure. And the entire process is also called representation learning. The network automatically learns the right features at each level of abstraction directly from the data. This hierarchy is why deep CNN works so well for complex visual tasks. Okay, this slide puts everything together. A CNN first focus on feature learning. So we apply like convolution to learn useful patterns directly from the image. After each convolution, we apply a nonlinear activation like ReLU, because real-world data is like always like nonlinear. Then we use pooling to reduce dimensionality and make the features more robust to small shift. By stacking these blocks, the network learns increasingly meaningful representation. Once the features are learned, we flatten them and pass them to fully connected layers. Finally, a soft maxed layer produces class probability for classification. That's like a classification problem. So CNN separate the problem into two different parts. First, like learn good features. Second, use those features to classify. I mean, the idea is still the same as like a neural network, right? But like you use the convolution to extract spatial information, to reserve locality and remove unnecessary information to build the classification model. So at the end of a CNN, we move from features to decisions. The convolution and the pooling layers have already extracted high-level features from the image. Then these features are passed into a fully connected layer, which combine them to make a prediction. Finally, we apply a soft max function. The soft max converts the raw output into probability, one for each class, and all probability adds up to 1, right? Because that's from statistics. Okay, so instead of just saying this is a car, the network can say that it has a probability of a car as 0.7, or like if it's a truck, we can say that the probability could be maybe 0.2, right? Then if it's a bicycle, the probability is 0.1, so it's not that possible, but it's highly possible to be a car, right? Based on the output here. The probabilistic output is what we used for classification and training. Okay, now the softmax converts the model output into probability for each class, as we mentioned before. So a higher value means a higher confidence in that class, right? Softmax give us a clean interpretable way to compare classes. I mean, if you just say 0 or not, it's hard, right? Because like sometimes like it could be a car or could be a bicycle. We just want a probability to give us a continuous way of representing that so that we can minimize during the training process, right? That's the reason why we select the softmax function. So this slide shows CNN, how CNN are trained in practice. We start with an input image. And of course, here is like a car. We pass it forward through networks. We have convolution, then like a ReLU activation, then pooling, and finally, fully connected layers with softmax. Okay, the result is here, right? So at the end, the model output class probability. We then compare those prediction to the true labels using a loss function, okay, shown here. As we mentioned, J is an objective function, or it's called like a loss function, right? So backpropagation computes how much each weight, both in the convolution filter and the fully connected layer, like contribute to the error. That's still the same using backpropagation to calculate, to minimize the loss, the control function. Okay, using these gradients, we update the weights to reduce the loss. This process repeats over many images until the network learns good features and accurate classifiers, more or less the same as like artificial neural networks. Okay, now to train like deep convolutional neural networks, we need large, diverse data sets, right? So ImageNet dataset is one of the most important image datasets ever created. So it contains over 14 million images across more than 20,000 categories. So each category is defined very precisely. For example, a banana is described not just as a fruit, but with detailed visual and visual characters. Some bananas are good, some bananas are bad, right? They are well like documented in this data set. People use this for like classification training. So here you can see many different images from different shapes, lighting conditions, background, and viewpoints even. So training on data like that force the neural network, the convolutional neural network to learn robust and general features, not just to memory the specific image. So ImageNet played a key role in showing that deep CNNs can scale and work extremely well on real world vision problems. Then the ImageNet challenge was a yearly competition designed to benchmark visual recognition systems. The main task was image classification. So giving you an image, the model had to predict which object represent. Okay, out of like 1,000 possible categories, could be apple, like banana, or more than fruits, something else, animals. So performance was measured using the top file error. That means like classification is considered correct if the true label appears in the model's top 5 guesses. ImageNet also includes other tasks such as object localization, object detection, and scene classification. The key point is that this challenge provides a standardized large-scale benchmark. It played a critical role in demonstrating that deep CNN dramatically outperformed previous methods, which led to the deep learning revolution in computer vision, I mean, a few decades ago. Now this plot shows how image classification performance improved over time on the ImageNet challenge. So on the left, we see classification error. I mean, lower is better, okay, of course. Before deep learning, error rate was very high, like around here, like almost like 30%. But in 2012, AlexNet was the first convolutional neural network to win the competition. It has 8 layers and about 80 million parameters, and it dramatically reduced error. Okay, now here, like half, almost 50% off, right? Now, after that, progress accelerated. The ZFnet improved AlexNet by using more filters. And VGG showed that deeper networks up to 19 layers performed even better. GoogleNet introduced like new architecture ideas with fewer parameters, and the ResNet made it possible to train every to train very deep neural networks over like 150 layers. By 2015 here, CNN achieves error rate lower than human performance on this task. See, like only 3%. This timeline shows how advanced in CNN architecture directly translated into better real-world performance. And this slide shows two trends side by side. On the left, we see classification error over time. Error drops dramatically from 28% in 2010 to below 4% in 2015. On the right, we see what makes that possible, much deep networks, right? You have like increasing number of layers. Our early model like had only a few layers. Over time, the network becomes deeper. With like a ResNet has more than 150 layers. Okay, the prediction ability dramatically improved. The key insight is that like depth really matters, but only if we can train deep network efficiently, not to overfit it. So architecture innovation like better initialization, normalization, and residue connection, those are like fancy techniques, also make it possible to go deeper without losing performance. Together, this trend explains why CNN is improving so rapidly. And now this diagram shows that CNN are not just for image classification. The left part of the network acts like a general feature extractor. It learned rich like spatial features of the image. What changes in the right part of the architecture? It like this. So for image classification, we add fully connected layers and softmax. Okay. For object detection, we attach detection heads like in RCNNs. For segmentation, we use fully convolutional networks that output pixel level labels. For image capturing, CNN features are passed into RNNs or transformers. So the same CNN backbone can support many different tasks. That's why CNN becomes a foundational building block in computer vision. Here, we have spent a lot of time like talking about CNN for classification, but now like what we have here is like, for example, in this image, can CNN understand like where and what of that image is like in this image, okay? Like in a much more complex way. And this is like a semantic segmentation, the where problem. So we want to find where that object is, and then like image capturing what that like image is and what is the story behind it. Now let's dive deeper into how we actually achieve that pixel level details. So we use what's called a fully convolutional neural network, convolutional neural network, FCN, or so it acts like unlike standard CNN that ends with a single label. Those networks are designed with all convolutional layers and inside two critical phases, downsampling and upsampling. Okay, so downsampling means like you have like an encoder. You encode this information down to a smaller sampling. So the first half of the process, we call it downsampling. We take our high resolution input. For example, here we have 3 times H times W, right? You have like red, green, and blue, different colors, right? You have 3 matrix. Then you have like height and width, okay? We pass it through layers that reduce spatial dimensions while increasing the depth of the feature. That's why you have multiple different layers of neural network, right? Okay. Then we go from high resolution to medium resolution, finally to low resolution, okay? We have a D3 times, okay, maybe like a quarter of H and a quarter of Y, a quarter of W. This capture what the core feature of the image. This is called like downsampling, or like in generative machine learning, we put it like encoder. Okay, then we also have another decoder part. You have to like upsample the image you already stored in the basic space, right? So we need a prediction that matches our original image size. This is where upsampling comes in. We take those low resolution features and project them back into a high resolution space. we reverse the process until we reach the final prediction, H times W. The final output isn't a single number. It's a map where every pixel is assigned to a class. In this case, identifying the specific pixel that forms the cause in the field. The architecture allows us to maintain the spatial context that is lost in traditional classification networks. Now, a real-world application. Here is a practical example, driving scene segmentation. So the map here, the model takes a raw street view and color-coded every element, distinguishing between the road, okay, the road is in purple, and the vehicles in blue, okay, and then like pedestrian in brown, okay. Now the complexity is like, so the legend on the right, you can have a look at this here. This allows an autonomous system to understand the precise boundaries of dozens of different environment class simultaneously. That's like what convolutional neural network is used in image segmentation. Yeah, any questions so far? Okay, great. That summarizes the session 2. It's more like a brief introduction to convolutional neural network and discuss its application in real world. Now, yeah, let's stop here and take a small break and come back later.
Then
Now let's continue. So the next session is for the lab, right? For the convolutional neural network lab. Okay, so yeah, we have that in the same folders on Pangeo here. So this is like convolutional neural network example. So now you want to play with this instrument and see makes sense to you, and feel free to reach out if you need any help for the next 1 hour. Yeah, they'll come back later for the final session. Yeah, then that's it. Okay, now then let's continue. Go back to our final session of today. The recurrent neural network. So let me go to my slides. Okay, so we have this session until 2:45, then we're going to have a break. So let's get started. Now, we're shifting to a new core concept, recurrent neural network, RNNs. So the big idea here is to use temporal context to improve our results. Instead of treating every data point as a separate event, we use the information from previous steps to refine our prediction at current time t. That's what a recurrent neural network, or RNN, is designed to achieve. Okay, so we use RNN for sequence learning, which focus on data that comes in a specific order. It's the order that is important other than the spatial structure alone. So in sequence data set, successive points are often dependent on each other. So example include letters in a word, or words in a document, or time series data shown like in this image here, or like frames in a video. Those are like time series data sets, and the order is important. So up till now, we often assume data was independent and identically distributed, or IID. Yeah, that's a term you see a lot in statistics. But for many real-world applications, this assumption seems not that correct, because like yeah, in reality, like identically and independent distributed is almost like I mean that's a very hard constraint to achieve. Okay, so standard CNN aren't great in this case. When the input or output changes in length, it's hard to define them because a CNN you already expect fixed 3D tensors, as we mentioned before. So we have an image, right? We have like a filter, and the filter is of like a fixed shape. And however, that like in reality, a sequence can be anything, like the difference between a short term, like I don't know, or like a much longer sentence. I know that you know that I know. So yeah, so basically they share the same thing, but like the sequence is important. In these sequences, the data points are strongly correlated with each other. Even though people have found ways to make CNN works for sequences, RN are often the priority choice for that. So let's look at a classic way to handle sequence autoregressive models here. The goal here is to predict the next term in a sequence by looking at a fixed number of previous terms. So in this setup, the output variable depends linearly on its own past values. As you can see in the formula YT here, we calculate the current value by weighing previous points like YT minus 1 and YT minus 2, and adding a bit of noise to the error, which is ET term here. It's basically a way of saying that to know where we are going to, right? We have to look at where we just went. That's like the autoregressive model. Now, another way to handle sequence is using feed-forward neural networks. These are basically a more advanced version of the autoregressive models we just saw, but they use nonlinear hidden layers to process the data here. You see like loss. You have a hidden layer here. You want to use this hidden layer to represent the sequence information. However, these are still like, they are just like memoryless models. They only look at a small fixed window of past words or data points. See here, like we only consider t minus 2. That means like only the previous 2 steps are considered. So it's memoryless, right? Because for memorable, like you want to maybe remember the things like in the first step, like initially you can move forward autographically. Like that's kind of a memory for a model we want to build. So because the window is limited, the model cannot really use a hidden state efficiently to remember long-term memory. Now we look at a linear dynamical system and hidden Markov models, HMMS. So unlike the last slide, these are memorable models. They actually have a hidden state here. This hidden state, you already keep track of what happened before. So in an hidden Markov model, the hidden state is discrete, meaning the model's transition between two different layers, like follows a specific and distinct way. These transitions and the outputs they produce are stochastic, which is just like a fancy way of saying they involve with the probability of randomness, and also with I mean determining a preferable like distribution. Okay, so while these are great for remembering context, they come up with a high time cost when the model tries to figure out exactly what the hidden state is at any time point. Okay, now let's get to a recurrent neural network by looking at this simple representation. So unlike the models we just discussed, an RN updates its hidden states here, right? In a deterministic nonlinear way. So you have an input right here, pass it to the hidden state, and the hidden state will pass output, of course. But this hidden state also passes information to the next like step, and this step like will also give you output and take the input of another information. So this, if you look at this diagram, you can see how information flows from one time step to the next through the middle hidden layer. This creates a chain-like structure that allows network to maintain a memory of everything that happened in a sequence in a specific order. Is any problem? Any questions with this diagram? Yeah.
So the diagram, it doesn't look like the inputs themselves have any relation.
Uh,
Is that intended? So
Right. This is just like a high level structure feature of expressing what an RNN is. So here, like these are like independent input. So they have different, for example, different word for this one and another word for this one. Sometimes like those words have some kind of correlation, but here we don't consider the correlation in this input. Instead, we consider the correlation in the hidden layer. For example, I want to have an apple, for example, okay? This word passed into this input, so this I will also pass to the next want, okay? You input want here, okay? This I is also passed to the want in the hidden layer. That's how like the correlation is built. Is that clear? Great. Any other question? Okay. Now let's get to next. So in a recurrent neural network, we update the hidden state in a nonlinear deterministic way, as we mentioned. So if you think about a simple speech example, the network take the word it just predicted and send it back as an input to the next like hidden layer. That's like how the example that we just like covered last time. So I want to have an apple, right? So I want to have an apple. It's not like clearly correlated in the input, but like instead in the hidden layer that everything like is connected. Now this diagram creates a chain where information flows forward through time, allowing the model to remember what happened at step 1 when it's at step 7. That's like the power of hidden state. Okay, now like how does an RNN learn? We use something called backpropagation through time. So backpropagation through time is still backpropagation, right? But depends on time now. Okay, despite the fancy name, it's just like a standard backpropagation process you already know. The only difference is that we perform it multiple times across the entire sequence. If you have a look at this unrolled diagram here, you can see how we trace error backwards from the final state HT, okay, all the way to the beginning H naught. This is just like a fancy way, like expressing like the diagram we showed before, right? You have input, hidden layer, output, right? So yeah, to make the representation simple, you just like put a circulation arrow here. This is how it is.
So A is the hidden layer now, and the H is already up.
Sorry. Yes, like this is like the output of the hidden layer, H. So you have the entire one is called like a hidden layer, right? You have an output H. If this layer is output, you call it like output. If this is just output of this hidden layer, we call it the hidden layer because we are going to have another layer, right? On top of it, like if yes, you have multiple layers. This is just like a one like a low level structure of recurrent mass. So this diagram basically allows neural network to adjust its weights based on information from the entire history of the sequence. Yeah, that's like why neural network work, why very recurrent neural network works. So now let's look at the math behind how information moves forward in this chain. Just like a standard neural network, an RNN works by repeatedly applying the chain rule. So as time moves from, for example, here, x0 to x4, you have it here. From x0 to x4, the model uses 3 main types of weights. Here you have like W in here, okay? This is a weight associated with the input data and W rec. Here, recurrent weights, plus the hidden state S, okay? The information to the step in the next, okay? And W out here, produce an error or output E, like for the specific moment. If you have like a additional layer here, then it just like H because the output of the hidden layer. If like you have no hidden layer anymore, you just want to output these numbers, then this is output layer. It's called like denotes with E. This flow allows network to maintain a continuous thread of information across the entire sequence. Any questions here? Yeah.
For previous thing, we just pick W once, right? Now you have to have three different W's, like W, graph, and also blah blah.
Yeah. So like, okay, let's
There you have a W.
let's start let's randomly pick. Don't pick like the first one because like can be ambiguous. Okay, let's go with the x2 here. Okay. So for example, like you have a data point, an input for x2, right? So for this input, I want to for 2, like I associate a weight. This is W in to this data. Okay, pass it to that hidden state. This is another neuron here, right? So like before, this neuron, you also get some information of the previous point, which is W rect is doing, okay? So you have input, of, for example, from x1, right? x1 pass the information to this x1. Then x1 gets some information about your input, and this input, like the information you get for s1 has two outputs. One is for like output layer E1, right? The other one is for the recursiveness. Like you pass this information to the next hidden layer state. That's why like you associate W recurrent to this neuron. Okay. And then like after like you combine this weight and this weight, right? Then you get like an output E2. And this output E2 is linked to another weight of W out. That's how this simple structure is meant for.
There's a bit of echoing. Not sure if you want to mute your computer. If there are questions, can you repeat that?
Okay, so what
If there are questions in the room, could you repeat them?
Oh, okay.
And there's a bit of
Got
echoing.
got it. Yes. Yeah, this they can't hear the question, so last time I'll repeat it. Like, yeah. So that people online can hear it. Okay, now we look at the backpropagation phase where we encounter a major challenge, vanishing gradients, right? So what is vanishing gradients? Any idea? Yeah, just as the name, right? As the gradient vanish, disappears over time. That's because like you have a long chain, right? When you pass the information from S0 to S4, as time went by, you pass the gradient one by one. The value could be like either very big or very small, right? For example, let's say that you have 2 times 2 times 2, okay? The weight is 2, okay? Let's say like this is a value of 1, okay? So the weight associated with this node is 2, okay? Now W rec is 2, you have like 2 times 2 times 2 times 2, okay? It becomes exploding, right? Over time. But if like you say like if your recurrent weight is 0.1, then as time went by, you have like 0.1 times 0.1 times 0.1 times 0.1. It becomes very small. So those gradients either get exploded or disappear. That's called like a vanish gradient. That's like one of the disadvantage of using RNA here. Its vanishing gradient make it very hard for model to learn long-term dependencies because the early parts of the sequence stops getting updated effectively. Now we need to address this. So this slide highlights the core issue with training standard RNN vanishing and exploding gradients. The problem happens because we multiply the exact same weight matrix W at every single time step during backpropagation. Yeah, I mean, like if you want to understand it, you can draw like a function, right? So let me draw a function here. So if I have like 2, this is 2, right? To the power of n, maybe we have a function looks like this, right? So as this is t, as time went by, as n went by, like you see like the function grows exponentially, right? So it will reaches infinity in the end very quickly. That's like oh yeah, question?
We don't, I don't think, I think only the Zoom people could see the.
Oh yeah. Anyway, like, okay, let's assume that, okay, let me try to,
Sorry.
I'll express it. So, for example, I can store something like exponential function, right? That you have basically up, right? If like it's like ex, you see like because the basis is greater than one, then the values like get grows exponentially. The result like gets big and big very fast. But if the basis is smaller than one, like right, then it's like a decreasing function, something will follow like this way, right? Decreasing over time. So that gradient decreases, just like a mathematical way of representing this vanishing gradient problem. Okay. So as you see, you can see in this diagram, when we try to pass information back through many layers from HT plus one to HT minus one, the gradient signal can get lost or become unstable. That's just as we explained before because of the function form there. Okay. Now let's talk about like bidirectional RNN. So in many types of time series analysis, we actually like have access to the future, like what you are analyzing in a full sentence or recorded video. So RNN, as we mentioned previously here, right? You're passing the previous information to the current state, right? That's like history to current. But bidirectional RNN says we also have information the other way around. You know the future. Okay, the future points, and you want to pass this information back to the initial, right? So this is bidirectional RNN. So as you can see in this diagram, it has two hidden layers, one for the forward state and one for the backward state. Here, by combining information from both the past and the future, the model gets a much better understanding of the context at any specific time t. That's like just a different way of representing RNN with two different hidden layers. Okay, as we discussed, standard RNN struggled because the memory decays or blows up over time. Okay. I think I need to wipe this in my figure. So how many people can see some graph I drawn before? Now I'm wiping it. Okay, now it works. Give me 1 second. Okay. Okay, so as we discussed, standard RNN struggles because the memory decays or blows up over time, right? So the most effective fix for this is the LSTM structure, long short-term memory. It's a structure for recurrent neural network. Think of LSTM as having memory blocks that acts like a digital computer. These blocks can read, write, and reset information using three special gates here, like the output, input, and forgot gate. This allows the neural network to decide exactly what is worth remembering and what should be thrown away. Okay, now let's have a look at the LSTM cell to see how it actually works. So unlike the simple RNN we saw earlier, an LSTM module is much more complex, containing four interacting layers. If you look at the diagram, the horizontal line at the top is the cell state. Okay, think of it like a conveyor belt that carries information through the sequence, right, with only minor changes. Now, the yellow box represent neural network layers, while the pink circles are pointwise operations like addition and multiplication here, right? Those things here. By combining these, the cell can carefully protect and control information, deciding exactly where to let through or block using its internal gates. This is like a single cell structure of LSTM module. Now, you might also see LSTM like schematized in a different form, like this diamond shape. It helps us visualize the gating process differently. So at the very center is the CEC. a constant error carousel. This is the memory that keeps the error signal steady to prevent it from vanishing. Surrounding it, okay, are three gates we have talked about. The input gate here, right? Oh, can I see my mouse? Yes, the input gate and the forget gate and the output gate. Each gate acts like a valve controlled by the small blue multiplication nodes, deciding exactly how much information flows into or out of the memory center. This setup is what allows the network to maintain a stable long-term memory while still being able to update itself with new inputs. Is there any questions with this representation? Okay, great. Let's move to next slide. So to wrap up how LSTM solved the memory problem, there are two key ideas to remember. First, the backbone. This is that straight horizontal line you see at the top, C t minus 1 to CT, okay, here. It acts like a highway that carries the state forward through times and allow gradients to flow backward easily without getting lost. Second, the gating. These are points where we use multiplication to control the information. By using a sigmoid layer, the gate output is always between 0 and 1, essentially acting like a valve that decides how much of signal to let go through. Let's break down the first internal step, the forget gate, represented by F here. Okay, so this gate decides how much of the previous memory we should actually keep or throw away. It looks at the previous state, the previous output, and your current input to make this choice. That's why you see you have like multiple different noise here and nodes here. For example, if the cell state was remembering that we have a subject in a sentence, it might forget that information once it finally finds the matching verb. So mathematically, it uses a sigmoid layer, sigma here, to output a value between 0 and 1. Of course, 1 keeps everything and 0 forgets everything, right? So next, we have an input gate represented by Y here. This gate's job is to determine which new values are important enough to update in our long-term memory, C. It actually works in two parts. First, the sigmoid layer decide what information to update, of course. Then a separate hypertangent layer here create a vector of new candidate values labeled as CT to be added to the state. Now together, these allow the cell to selectively add only the most relevant new information to its memory. Now we combine everything to see how the cell state C actually updates. So first, we take the old memory and run it through the forgot gate. So we have like ft times c t minus 1, right? To drop what we don't need anymore. Next, we take the new information from the input gate here, like it times the ct, and add it to that state. These create our new update memory CT that will be passed on to the next step in the sequence. So essentially, we are performing a point-wise modulation to keep our long-term memory stable and relevant. The final step in the LSTM cell is output gate, represented by O. So the gate decides what part of our internal cell state actually get passed on to the current output H. It uses a sigmoid layer to determine which part of the cell state we are going to output, and then run the state through a hypertangent layer to push the values between like -1 and 1, right? So for example, it could decide to focus on whether a noun is singular or plural to prepare the network for the correct verb form. And the most important takeaway is that we don't manually design these rules. The network learns these pictures on its own through training. This is summarized like the three key structure of LSTM cell. Now to wrap everything up, let's look at how these two models actually behave over a long sequence. So in the first diagram, right, you have like when you have regular RNN, it suffers from the Vannish gradient problem. The shaded shows like a sensitivity, right? The further we get away from the start, more network forgets the original input because the signal decays exponentially, right? If we set the weight smaller than 1, then it decays, okay? That's why like it becomes like less and less black. Now, let's look at the STM in the right. So notice how those nodes stay dark even at step 7, right? Step 6 here, right? You still have like black points. That's like how information from the initial point is passed on to the even like the last point. So because LSTM can selectively open and close its gates, it can preserve the early information throughout the entire sequence without it fading away. This is why LSTM are so much more efficient for tasks where long-term context really matters. Yeah, that's basically this basically so far summarize all we have for the recurrent neural network. So any questions so far? Okay, great. Now we have time for break. Then after the break, 15 minutes, we come back to do the lab. So the thing is still like you understand the high level structure of STM, of the recurrent neural network. The math behind it, like it takes time and takes, I mean, huge efforts to understand it. But like that's not the target for today, right? Because like you're going to cover more courses on STM, RNA in the future. But today, I hope you will get like a rough understanding of how things work for LCM and how RNA is doing and propagate over time. And you understand how to use the code for it, then that's it. That's the target for today. And I hope you enjoyed it. I'll see you later. Okay, so we're prepared. Okay, let's wrap up with our final thoughts about generative AI. So the main goal here, like for generative machine learning models, is to create a probability distribution, a PX, like that mimics the patterns found in real data samples. We call them generative because we use the distribution to generate a brand new data set that looks just like the true statistics sets either behind generative machine learning models. There are several popular generative machine learning models, like you might recognize such as the first one, like variational decoder. I think that's like the first deep learning 101 model I learned, like autoencoder. Then after that, like Professor introduced variational autoencoder. That somehow like, you can encode your latent space somehow and predict an element image. Then you also have some generative adversarial network. Yeah, they are also very popular. I mean, before like diffusion model. Diffusion models, I think in 2018 something, that like this model becomes like even ChatGPT nowadays, like diffusion model dominates a lot in image generation. And also, of course, you have the automatic flow model. Automatic flow models like I'll show you a picture here. So that's the difference comparison between different generative machine learning models. For the normalizing flow model, like I mean the mirror is like they have a very elegant piece of math. You can write the generation or encoding process through a set of mathematical gradient looks beautiful. And the first the top image here shows like again models of very much similar to the variational autoencoder. Okay, so let's talk about variational autoencoder first. It's kind of like similar to convolutional neural network, right? It's used for image process. You have like input data, somehow like you shrink the size to, we call it an encoder. If we reach it in the space Z here, then we have a decoder trying to decode the information from the latent space back to the original image and one the generated image here. similar or identical to this image as much as possible. This is like identifying the generative model. We call it generative because in this later stage, we have some kind of control of the function form. So that after training, we can always start from the latest stage to generative rate. That's why we call it later stage generation or like generative model. So similar to the variation of the encoder we have got here, okay, we can look at here. So somehow similar but different. Okay, the ground is that you have a discriminator and you have generator. You constantly try to make sure the generator somehow can discern the difference between the true data and the discriminator. That's the high level idea why GAN works. Now, regarding flow model is like you use a set of like gradient and take the derivative all the way back until you reach a generator. Make sure that these two data converges are identical to each other. That's like the flow-based model. And now, like the diffusion model, we keep adding noise until you reach a selected space, and you have a generation process going back. Okay, the flow-based model is like bidirectional, right? So in the training process, it's like you go from the original model to a latent space Z. Okay, go this direction. Okay, then like the generation process is like the other way around. Okay, you go from the latent state, go up to the original image. Similar to for the diffusion model, you go from this way. Okay, then for the generation process, the other way around. Those are just like some examples of machine learning, generative machine learning model. We don't want to run deep of it. So it's like here topic also we just want to have some coverage with this. Okay, now like to really understand these models, let's have a look at the core mission here. So we have the latent space here, right? So we start from a simple random distribution PZ here. We then feed the noise through neural network. We have like GZ equals X. Okay, the goal here is for the network to transform that noise into the new data samples, like the image of the trees or cats or birds that look almost identical to the real scene. If the model is trained well, then it learns to map that random input into a space that perfectly matches the distribution of the real world image. Those are just like example of how why it works. So let's talk about conditional generative models here. So in the last slide, we just generated random images, but here we add a specific condition to the neural network, like running block. So we start with the same random noise distribution Z, but we also feed the network specific parameters to guide it. Then what the network then use both the noise and the condition to generate new data sample that matches your request. As you can see, output X here isn't just a random animal, it's a variety of thoughts that are specifically in motion, closely resembling the real distribution of running blocks image. Okay? That's why, for example, like in those image generating models, it works for okay, if I want a running block, I give this condition to those models, and can generate the block and that is running, right? Different in the beginning, we say that if we don't keep this condition, but we start from the randomness in the base latent space where it generates random image of the image somehow can mimic the input image. And now to train these generative models, we often use a technique called maximum likelihood estimation (MLE). This is just like a high level abstract mass function. So the idea here is to estimate the best parameter for our model by maximizing what we call likelihood function. The function basically measures the probability of seeing our observed data given specific parameter values. As you can see in this diagram, we want our network's generated distribution to overlap as perfectly as possible with the real data distribution. Okay. By maximizing this likelihood, we are essentially forcing the model to become like a better emulator of the real world. This is like the math technique. But of course, like in reality and in like a theory is more complicated than this. But today we just like have a rough understanding of it. So it's maximizing the probability like of the generated data set, right? To make sure that this probability converges to the true data set. That's like the high level idea for all the generative models. Yeah, then yeah, basically that's it for today. So to wrap up, I would like to show you this image here. Yeah. So next time in the future, like if you see any generative AI models, you ask yourself, okay, what kind of models like they are based on, and whether they are able and we prove it. Yeah, then thank you so much for your presence today. I really appreciate it. Thank you to teach you and interact with you. If you have any questions in the future, feel free to email me or send me in the channel. Yeah, I'm so happy to be participating.